The Napier Nomad I is likely the most complex aviation engine ever built, which turned into the only slightly less complex Nomad II that utilized a brilliant concept called turbo compounding, which recovers energy from exhaust gases to boost engine power. In this video, I'll be explaining the engines and the utilized concepts as simply as possible. The Second World War just ended, and the rush to squeeze ever more power out of large piston engines has virtually come to a halt due to the emergence and great promise of turbojets and turboprops. Napier had accumulated a wealth of knowledge on high-power piston engines during the development of the highly complex and troublesome, but eventually successful, H-configuration 24-cylinder Sabre. They also gained knowledge on arguably the most fuel-efficient piston engine type for aviation applications, the two-stroke diesel, when they license-built the Junkers Jumo 204 and 205 as the Napier Culverin and Cutlass respectively from around the mid-1930s. I've covered the Jumo 204 and 205 engine design in great detail in this video, which I encourage you to watch after this one. Just before the end of the war, the British Ministry of Aircraft Production, who later became the Ministry of Supply, issued a requirement for a new engine of 6,000 horsepower with the best possible fuel economy for long-range aircraft. Napier was well placed to pursue, especially given the previously mentioned expertise. Legendary engineer Sir Harry Ricardo suggested that the best way to create a both powerful and economic engine is by combining a gas turbine with a two-stroke diesel. So that's exactly what Napier did. After Napier briefly experimented with the idea of a Sabre-esque 24-cylinder, 75-litre or 4,575 cubic inch engine with a recovery turbine, codenamed the E124, they instead came up with this. Other than cutting the cylinder count in half, it remains quite a complex behemoth with contra-rotating propellers to boot. Here's the quickest way to describe what this is. Instead of having combustion happening like normal in the continuous burn combustion chamber you'll find on gas turbines, they instead used a diesel engine to handle combustion. But why complicate it? Why not just use a gas turbine? A gas turbine works on familiar internal combustion engine principles: intake, compression, combustion, and exhaust. Air enters at the front and gets compressed by an axial compressor, which is multiple spinning rotors with stationary stators between them that progressively pressurize and heat the air. This compressed air enters the combustion chamber where fuel is continuously injected and ignited, unlike a piston engine's periodic combustion. The hot, expanding gases then spin a turbine as they exit rearward. This turbine powers the compressor to keep the cycle running. In a turbojet, the expanding gases create thrust directly. In a turboprop, the turbine also drives a propeller through a reduction gearbox, with the propeller providing most of the thrust. However, gas turbines in the late 1940s were much less fuel efficient than piston engines, mainly due to material limitations that restricted how hot combustion could run. To maximize thermal efficiency, you want the biggest temperature difference between the compressor inlet and turbine inlet after combustion. The hotter the combusted gas is entering the turbine, the more expansion work is available and the more efficient the engine. However, with late 1940s materials, turbine blades had temperature limits around 1500 degrees Fahrenheit that couldn't be exceeded without damage. Diesel engines, on the other hand, achieve much higher peak combustion temperatures, over 4000 degrees Fahrenheit for an instant. Combined with very high compression ratios, this allows more complete energy extraction from the fuel. This is why Harry Ricardo suggested that combining a turbine with a diesel engine would be much more fuel efficient. In effect, what they did with the Nomad engines was replacing the very inefficient turbine combustion chamber with a two-stroke diesel engine which handles the combustion process. Now let's look at how Napier actually made this work in practice. If we look at the simplified illustration of the Nomad I, it reveals some details. Air enters an 11-stage axial compressor, which collectively is the first stage of intake air compression and produces a 5.62 to 1 pressure ratio increase. Air is then fed into a second stage of compression, a centrifugal compressor, which is basically a supercharger. Feel free to ignore the intercooler, which wasn't implemented. After the 2 stages of compression, airflow was split by ducts to each bank of inline 6 cylinders where air was forced into the cylinders. It's a 41-liter 2-stroke compression ignition engine, meaning it doesn't use a spark to ignite the compressed air and fuel mixture. Instead, it compresses and heats the air so much that injecting fuel into it is enough to start combustion. No spark needed. It's a liquid-cooled, horizontally opposed 12-cylinder engine. Unlike modern boxer engines, this flat 12 uses shared crank pins like a V engine, essentially a 180-degree V configuration. 4 blade connecting rods were used, allowing the opposed cylinders to be perfectly aligned. The 2-stroke design enabled lightweight, slipper-type bearings. Since 2-stroke engines fire at every top dead center, all piston movements are a result of combustion pushing the piston down or from the crankshaft pushing the piston up. There are no pull loads like in 4-stroke engines. This unidirectional loading meant half bearings were sufficient, reducing weight and material costs. A 6-throw crankshaft was used, with crank pins separated by 60 degrees of rotation, giving it a 60-degree firing interval. So, 2 cylinders, 1 on each side of the engine, were fired at the same time, every 60 degrees of crank rotation. As a result, the 2-stroke flat 12 was perfectly balanced, as each pair of pistons had another pair 180 degrees out of phase. To prevent dangerous torsional vibration in the event of something like a fuel injector failure on a cylinder, a torsional damper was fitted to the rear end of the crankshaft. While petting Mr. Snuggles here behind me, this is a good pause point to give a massive thank you to the Napier Power Heritage Trust, and especially Nigel Payne, archivist at the NPHT, who supplied me with these amazing photos of the Nomad, most of which are not available on the internet, and for giving me permission to use it in this video. Without it, this video would be rather bleak on the visual aspect. Please visit their website, which is also linked in the video description. Back to the video. The crankshaft spins one of the propellers via a reduction gear. With Napier being famous for their sleeve valve Sabre engine, it's important to note that the Nomad didn't have sleeve valves, or any valves for that matter. As the pistons reciprocated, they exposed ports in the cylinder walls for intake and exhaust. It's a loop scavenge system. The intake ports are created in a way that intake air is routed upward, following the cylinder wall, looping around the hemispherical combustion chamber, and then down towards the exhaust ports where it exits. The exhaust ports are located slightly higher up in the cylinder than the intake ports to ensure that as the piston descends, the spent gases start exiting before fresh intake air is drawn in when the intake ports get exposed. For proper scavenging, a 2-stroke diesel requires a supercharger. And the Nomad I did have one of sorts. The gas turbine centrifugal compressor effectively acts as the supercharger, as it's gear driven by the engine, but we'll get to that now. Exhaust gases then exit via the exhaust of each cylinder, and the 12 exhausts all merge at the rear of the engine. Here, the expanding hot gases spin a turbine, like a turbocharger, but this is a 3-stage turbine, and it also creates thrust, like a turbojet. However, since the 3-stage turbine extracts the maximum amount of energy from the gases, the thrust created is not that much. The turbine is connected to and spins the axial compressor, which draws in fresh intake air, and it also spins the second propeller. To provide additional thrust for takeoff, the engine also had a primitive afterburner of sorts. In the exhaust between the engine and the turbine was a mini second combustion chamber where fuel could be injected and ignited to increase the exhaust gas flow. Opening a valve then permitted gas to flow past a secondary axial turbine located in front of the main turbine and connected to the same shaft. This allowed the engine to create more power, which could be used at takeoff. The Nomad I is basically two engines in one, with the piston diesel taking care of combustion, turning one propeller and a supercharger. And then the exhaust gases spin the turbine, which in turn spins the axial compressor as well as the second propeller. The two engines could not operate independently from one another as both require the combustion process of the diesel engine. How neat is that? And it wasn't just a theoretical idea. The engine was built and ran for over 1,000 hours, including powering a modified Aero Lincoln bomber. It produced 3,000 shaft horsepower, which was 1,450 horsepower from the diesel engine and 1,550 horsepower from the turbine. In addition to that, it also created 1.42 kilonewtons of thrust at the exhaust nozzle. As it may not be clear if that is a lot or not, the ME262's turbojets created 8.8 kilonewtons of thrust each. The engine was reported to be very temperamental, however, and it was an overly complex monster of an engine. Weighing in at 1,905 kilograms, it weighed triple that of a comparable turboprop engine. Even so, it achieved a specific fuel consumption of 0.36 pounds per horsepower hour, matching the much less powerful Yumo 205. Comparable turboprops of the time achieved around 0.55. The Nomad I's complexity and temperamental nature, however, prompted Napier to consider something less complex but much better. Enter the Napier Nomad II. Looking at the simplified illustration of the Nomad II, it looks a bit less complex, but it utilizes turbo compounding, which we'll get to in a minute. The Nomad I's centrifugal compressor, the second turbine, afterburner or auxiliary combustion, and the contra-rotating prop were removed, so only a single propeller remained. An additional stage was added to the compressor, increasing pressure ratio to 8.25 to 1. Here's how the Nomad II differed from the Nomad I. The simplified design used a single 12-stage axial compressor feeding the diesel engine with exhaust gases driving a turbine that powered the compressor. The crankshaft drove the single propeller through reduction gearing. But the real innovation was solving a fundamental problem. The exhaust-driven turbine doesn't have the power to turn the compressor at low crankshaft RPM. In this case below 1,500 RPM. For this reason, the Nomad I needed a supercharger or crankshaft-driven compressor. But removing the supercharger on the Nomad II meant it couldn't perform its job of scavenging at low RPM. How would the engine even start? Remember, it's a two-stroke diesel engine. It needs pressure to force spent gases out of the cylinder and force new air in. But the axial compressor could do the job of assisting scavenging on the Nomad II, as it was not only connected to the exhaust-driven turbine, but to the crankshaft as well, and this was done through what's called a Bayer coupling. This is almost like a torque converter you'll find in a car with an automatic gearbox, using hydraulic fluid to transfer power between input and output shafts without a fixed mechanical connection. But it's quite a bit more complex than a torque converter because it's a three-way connection between the crankshaft, the turbine shaft and the compressor shaft with bidirectional power flow and has an infinitely variable gear ratio. This way, at low RPM, when the turbine isn't producing enough power, the crankshaft turns the axial compressor, which can now do its job of scavenging the two-stroke diesel engine at low RPM. At high RPM, the turbine is creating enough power and the coupling allows it to turn the compressor. But, in fact, at high power, the turbine is actually creating too much power for the compressor. Normally, like with a turbo, the excessive boost pressure could be released via a wastegate to prevent turbine overspeed, but that wastes energy. On the Nomad II, they wanted to utilize as much exhaust gas energy as possible, so it did not have a wastegate of any sort. So, how did they prevent turbine overspeed? This is where turbo compounding comes in. At high RPM, when the turbine created excessive power for the axial compressor, it fed the excess energy back into the crankshaft, which was done via the Bayer coupling. This fluid coupling naturally balanced the system. Excess turbine power automatically flowed to the crankshaft. Since the turbine now helps turn the crankshaft, the diesel engine is doing less work and is thus consuming less fuel. The Bayer coupling with its infinitely variable gear ratio also sorted out the speed difference between the turbine, which could spin up to its maximum speed of 18,200 rpm, and the crankshaft, which turned only 2,050 rpm. At the front of the engine, the propeller speed was reduced around 0.6 to 1 by a spur gear prop speed reduction unit. Here, two coil shafts connected and extended backward, the upper one towards the Bayer coupling and the lower one towards the turbine shaft. The Nomad II's specific fuel consumption across common cruising speeds and altitudes was less than 0.35 pounds per horsepower hour, with best possible efficiency being 0.326, which was achieved cruising at 22,250 feet. That is very impressive, not only for the time, but even by today's standards. I'm not aware of any modern aviation engine that matches that. If I missed any Aero engines that actually ran that came close to that number, let me know in the comments. The specific power of the Nomad II was 1.25 shaft horsepower per cubic inch, and it had a power to weight ratio of 0.88 horsepower per pound. The power split between the diesel and turbine looked like this. The diesel engine alone produced 2,660 horsepower at 2,050 rpm. The turbine produced 2,250 shaft horsepower, but 1,840 of that horsepower was consumed driving the compressor, with another 20 or so horsepower lost to the variable gear coupling. While most of the turbine's power goes to driving the compressor, this actually frees up the diesel engine. Normally, a piston engine of this power would need to drive its own supercharger, robbing power from the crankshaft. The Nomad's exhaust driven turbine handles this job while still delivering an additional 410 horsepower. Adding the small amount of jet thrust it creates, total output reached 3,135 shaft horsepower. On the Nomad III design, the afterburner or auxiliary combustion from the Nomad I was brought back. By injecting and igniting fuel at the exhaust manifold between the engine and turbine, it created additional power. Using this in addition to water injection, takeoff power could be increased to 4,100 horsepower. Unfortunately, the Nomad III was never built. The Nomad II was first run in late 1952, ran for several hundred hours in testing, and was to be installed in a modified Aero Shackleton for flight testing. Ground runs were done, but the engine program was cancelled in early 1955 before any flight tests could happen. So, why was it cancelled? It was a high-power engine with extremely low fuel consumption, exactly what the world needed. But was it really? Several things kept the Nomad II and III from ever seeing mass production. The Nomad II weighed 1,620 kilograms. That's much lighter than the Nomad I, but more than double that of a comparable turboprop. This would eat into the useful load of long-range aircraft. Another important reason is the time the requirement from the Air Ministry came, which was around 1945. Things changed very quickly in the years that followed. The Nomad engines delivered exceptional fuel efficiency, but as alien as it sounds today, in the post-war years, fuel efficiency was not a top priority. In fact, then it was seen as a somewhat negligible advantage. Here's an example of this. Ernest Chatterton, chief engineer at Napier, gave a lecture in 1954 about the Nomad. Present at the lecture was Air Commodore F.R. Banks, who was Principal Director of Engine Research and Development at the Ministry of Supply. He remarked that, when comparing different engines, they should not be overly concerned with specific fuel consumption. The context was simplicity of design versus fuel efficiency, which were on opposite sides of the spectrum. It would not be until the 1970s oil crisis before fuel efficiency would start to really matter in the world again. Something else to keep in mind is, even with the Nomad's superior fuel efficiency, it drove a propeller. Propellers lose aerodynamic efficiency at higher altitudes, where efficiency for turbojets massively increases. That also made propeller aircraft comparatively slow. While a Nomad II powerplane would have much better endurance than any turbojet, it wouldn't necessarily have much better range. See, total fuel consumed on any given flight is a function of fuel burn per hour times the number of hours flown to reach the destination. Even though a turbojet consumes much more fuel per hour, the flight duration would be less as it flies a lot faster. So the turbojet plane is burning fuel for fewer hours than something like the propeller-driven Nomad. Let's also not forget, the Nomad wasn't production ready and needed a few more years of development. But after the more than £5 million already spent, the Ministry of Supply was no longer willing to continue funding the development of the Nomad. For applications where turbojet or turboprop fuel efficiency weren't adequate, it turned out much cheaper to use some of the existing high-power, less fuel-efficient piston engines from the previous decade than to continue the development of the Nomad. An example of this is the Aero Shackleton that used 4 Rolls-Royce Griffons, which was used operationally by the RAF until 1991. Adding the significantly higher weight of the Nomad, the much higher complexity and maintenance that goes with it, the Nomad couldn't compete with turbojets or even turboprops on anything that mattered at the time. A brilliant invention it was, however, even if it was an engine out of time. And if only turbo compounding could be done with less complexity, I think the aviation world could be a different place today. So, was the Nomad the most complex aero engine ever created? Or is there an engine I'm forgetting? And was the Nomad the pinnacle of piston engine development? Let me know in the comments. I'd love to know what you think. Thanks for watching. See you in the next one.